Hello, everyone. My name is Lecheng from University of Illinois at Urbana-Champaign. Today, I'm going to present our recent work, Deep Co-attention Network for Multi-View Subspace Learning. This is a joint work with Dr. Cheng from Microsoft Research, Dr. Hongxia Yang from Alibaba Group, Professor Nan Cao from Tongji University, and my advisor, Professor Jingrui He from UIUC. In our daily life, we are exposed to the heterogeneous data. Usually, the data are collected from multiple source domains and thus exhibit the view heterogeneity. For example, in social media, a post may include both the text data and the image data. In the medical domain, the images of brain can be taken at different positions, and each image can be considered as a single view. In financial domain, the dataset could consist of both the numeric data, like the stock price, and the text data, such as news. To address the multi-view problem, many state-of-art algorithms has been proposed. However, one important drawback of the existing method is the lack of interpretability, as it's important for some decision maker to understand why the model makes such a prediction. For example, 3 brain images of the same patient are fed into a deep model, and the model provides the probability of this brain-related disease. However, to trust the prediction, the doctor needs to know why the model makes such a prediction. Some of you may ask, can we directly apply the existing interpreted machine learning algorithm to explain the prediction? Well, to answer this question, let's look at the example below. Given a sample with 2 views, if we use the interpreted model to capture the features that are most related to the white bird in these 2 figures, it's very likely that the feature captured by the interpreted model in these 2 views are inconsistent, as the interpreted model may accidentally include the noisy features for interpretation. On the other hand, utilizing the consensus information of multi-view data could potentially help us build a more robust interpretable model against these noisy features. In particular, our work aims to answer the following 2 questions. First, can we extract both the shared and view-specific representation of multi-view data for final prediction? The second question is, can we utilize the consensus information of multi-view data to build a robust interpretable model against the noisy features? And here is our outline. We have finished the introduction. Next, we will begin to introduce our proposed method, which is followed by the experiments. And finally, we will make a brief conclusion. To begin with, let's first look at the notation. In this table, we use D to denote the dataset. Xi is the ice view of the input feature. Y is the label matrix. N is the number of samples. Di is the feature dimension of the ice view. V is the number of views. C is the number of classes. Px1 is the data distribution of the first view. For ease explanation, we will focus on 2-view setting, so our proposed method could be applied in more than 2-view setting. So here is the overview of our proposed method. The figure on the right-hand side is the structure of the proposed method. Specifically, X1 and X2 are 2 views, which will be fed into 2 encoders, G1 and G2 separately, to produce the shared representation Z1 and Z2. And Z1 and Z2 are also the input for the discriminator D. If the input of the discriminator D is Z1, then the discriminator will output true. If the input of the discriminator is Z2, then it will output false. The F1 and F2 here are 2 decoders, which aims to recover the 2 reconstructed views. The difference between the original feature, X1 and the X1 hat, give us the view specific for the first views, S1. Similar way to get the view specific information for the second view. The combination of the shared feature Z1, Z2, and the view-specific information S1, S2 are used to feed into the classifier to make the final prediction. Next, we are going to focus on 3 modules: Encode Module, Discriminator Module, Decoder Modules, and we will elaborate them one by one. The first module is Co-attention Encode Module, whose goal is to explore the coloration of each pair of features and to select the most important features. Before we introduce the Encoder module in detail, let's look at the data preprocessing. For the i's view of J's sample denoted as xij, we are going to split it into ki segments. For example, if xij is image data, we could use the image partition algorithm, such as mask RCNN, to split it. If this view is the text data, we could use the word vec to get the segments. Now we are ready to introduce the Encode module, which mainly utilizes the co-attention mechanism to measure the importance of each segment. The figure on the bottom right corner is the structure of the Encode module. Suppose we are given a sample with 2 views, x1j and x2j. First, we could feed these 2 views into 2 neural networks, Q1 and Q2, and get the hidden representation M1j and M2j. Then these 2 representations are used to compute the affinity matrix C12j. This affinity matrix captures the coloration of different segments in 2 views. After we get the affinity matrix, we could use nonlinear transformation to get the hidden representation H1j and H2j. Notice that in these 2 equations, H1j and H2j contains the information extracted from 2 views. By utilizing the information from these 2 views, we could reduce the potential negative impact of the noise feature when building an interpretable model. Then, the attention vector A1j and A2j are the softmax of the linear transformation of H1j and H2j. This attention vector A1j and A2j are used to determine which features are the most important features. And we also use this attention vector and the representation M1j and M2j to compute the final shared representation Z1j and Z2j. The second module is the Discriminator Module, which aims to help the Encode module find the shared representation in adversarial setting. Below is the objective function to extract the shared representation in adversarial setting. Basically, it involves the computation between the discriminator D and the 2 encoder G1 and G2. The intuition of this module is that the discriminator D aims to maximize the probability that the given representation is generated by the first encoder rather than the second encoder. The encoder G1 and G2 aim to minimize such a probability. And with this adversarial chaining, we want to ensure that the extracted representation only contains the shared information. The last module is the Decoder Module, the goal of which is to extract the view-specific information. Below is the loss function to regularize the view reconstruction, which consists of 4 terms. Each term is the difference between the original feature and the reconstructed feature. So here in this equation, x hat ij is the recovered i's view based on the j's view. It means that we use the representation extracted from j's view to recover i's view. For example, if we use the encoder J2 to generate the shared representation Z2, then the encoder F1 and F2 should be able to transform Z2 back to both X1, the first view X1 and the second view X2. In other words, we could use the shared representation to reconstruct all views, no matter what encoder generates this representation. With these regularization terms, the difference between the original feature and the reconstructed feature give us the view-specific information. In this equation, the gamma 1 and the gamma 2 are the 2 constant parameters to regularize the weight of this reconstructed regularize the reconstructed feature. With these three modules, we could formalize the overall objective function, which consists of three terms. The first term is the constraint that helps the encoder module find the shared representation. The second term is a constraint that extracts the view-specific representation. And the last term is a cross-entry loss. And in this equation, alpha and beta are the constant parameter balanced in three terms. The extension to multiple view setting is omitted for the time limit, but you could refer it in our paper if you are interested in our work. So next, we are going to show the performance of our proposed method. The effectiveness of the proposed method is evaluated on phi dataset, and this table shows the statistic of this phi dataset. We compare our proposed method with the following baselines, including a sample deep neural network, some CCA-based method like linear CCA, deep CCA, DCCAE, as well as a deep multi-view learning method, namely deep IB. And here is the performance comparison on 4 dataset. You may refer to our paper for more experiments. So in this experiment, we evaluate the performance by the metric of F1 score and accuracy in some classification tasks. In these two figures, the light blue bar is the performance of our proposed method. We could observe that our proposed method outperforms all baselines in terms of these two metrics over 4 datasets. In addition to effectiveness measurement, we also conduct a case study to show the interpretability of the proposed model. Specifically, the goal of this case study is to interpret the prediction results and provide the relevant clues for the decision maker to investigate the vulnerability of the proposed model in the noise environment. The experiment is conducted on the Caltech bird dataset, and the figure below is a demonstration of the interpretability of our proposed model. The first column is the original feature of two view, and the next three columns are the segments extracted by the image partition algorithm, which is masked RCNN in this experiment. This bar chart shows the importance of the three segments in two views. Notice that the A1 and A2 here are the attention weights, which measure the importance of each three different segments. These classification tasks aim to predict the apertures, the white bird in these figures. And by observation, we could find that our proposed method assigns the largest weight to the first segment of the first view and the second segment of the second view. So finally, we are going to make a brief conclusion. In this work, we propose a deep model which integrates both the shared and the view-specific informations. And it also utilizes the co-attention mechanism to provide the robust model explanation. To demonstrate the effectiveness of the proposed method, we also evaluate the performance of the proposed method over 5 real-world datasets. We also conduct a case study to show the interpretability of the proposed method in the noise environment. Thank you for listening.